was not attracted by this xi of t. So it's another way of rewriting this probability is to say that gt of e to the ix is not equal to xi t until time t. Okay? So gt of e to the ix, it's something e to the ix is on the boundary of your disk. The boundary is sent to the boundary. So here, so here, this thing is on the boundary, on the unit disk, and this is on the unique disk. So somehow you already see that this was a two-dimensional problem, and now this is a one-dimensional problem. So somehow what we are going to do now is really make sense of that. Transform this problem into a one-dimensional problem, so in terms of diffusions, and solve simply this diffusion in a straightforward way. So let's rewrite this like this. So gt of e to the ix, I will rewrite this as xi of t e to the I y of t. So I define y of t like this. And this is well defined because this is something on the unit disk. This is something on the unit disk. Both are continuous. So perhaps I should have said that. So in the case of radial SLE6, this is square root e to the I square root of 6 bt, where bt is the Brownian motion. So these two things are on the unit disk, so this is well defined. There is a y like this. And what I want to prove now is that this y is a nice diffusion that I can study. And what I want for this y is that it's never equal to 0 or 2 pi. This thing must be always different from this, which is equivalent to say that e to the I y x of t is not equal to 1. And this is equivalent to say that y x of t does not belong to 0 or 2 pi. So let's say here, at time 0, y0 of x is x. So I have a diffusion, something continuous, starting at x, and I don't want it to hit 0 or 2 pi. That's the only problem I have. This thing boils down to this question. So if you have a diffusion and you want to look at its surviving time, you need to know what is exactly the diffusion. So the first step to do is to try to compute the derivative of your diffusion and to look at, and after we will be able to look at the survival time of this diffusion. So here the moral is yxt is a continuous diffusion between 0 and pi, and 2 pi. So ready? We have 0 and 2 pi. And we want our diffusion starting at x to remain between 0 and 2 pi until time t. OK. So here, we have a definition for this yx of t. So we can just use the definition and the Loeffner equation to derive the derivative of this. And that will be always the case. I mean, you will be, once you have the diffusion in your hand, everything is straightforward. What is not completely obvious is to find the diffusion. But in this case, it's straightforward. So let's take the logarithm of gt of e to the ix. So here, when I mean by logarithm, I have to be careful because I'm on a domain with 0 inside. But let's say that locally, you can define the logarithm. So let's take the logarithm, which is local definition. So the logarithm of gt of e to the ix is the logarithm of c of t, which is equal to this, plus e to the y xt. So if I want to compute d of y xt, it's minus square root of 6 d of bt plus, so plus 1 over I, so minus I, so minus the derivative of the logarithm of gt of e to the ix. I just differentiate what was above. Okay, so here I don't have really the right to differentiate on the boundary because I didn't prove you that this Loeffner equation was true up to the boundary. But because the boundary is smooth, that's true. Somehow you can compute this for z inside the domain and after push z to e to the ix because you are on a nice part of the boundary, everything works fine. So this is the thing we want to compute. Okay. So when you look at this, you know how to derive this. That's the derivative with respect to t of gt prime of e to the ix over gt of e to the ix times dt. Derivative of the logarithm. And so now this thing I can replace by what it is equal to there. Derivative, yes. So this is equal to that, to minus that. So this is equal to minus gt of e to the ix plus c of t about gt of the e to the ix minus c of t. This is just due to Loeffner radial equation. Yes? No, everything is purely imaginary above, because this is something on the boundary. Gt of e to the ix, because e to the ix is on the boundary, it's sent to a point on the boundary. So, I mean, the logarithm is tricking you. It's a purely imaginary thing. So if you prefer, you can take the imaginary part everywhere, but it's useless since it's already purely imaginary. But that's a good question. A priori, we don't know that. But here, it's the case. OK, so, I mean, OK. So let's write this here. I wanted to make one computation, and that will be the only one, please, to show you how do you do that, to show that there is nothing hidden here. I mean, this is straightforward math. So this is equal to minus square root of 6 dbt. There is a minus and times a minus, so it's a plus. And now if I replace gt of e to the ix by c of t e to the I y x of t, I get that the second thing is equal to that. I just replace this by this, and I divide it by c of t above and below. And there is still the dt here. And this, if you rewrite it carefully, it's just the cosine of yxt over 2 over the sine of xt over 2. What we usually call the cotangent. Yeah. Okay? So the moral in the story is that we had a two-dimensional problem. We translate it in terms of a diffusion here. And this diffusion, we know what it is exactly just using the Loevner radial equation. The Loevner radial equation, it allows you to compute the derivative. So now we just want to compute the surviving time of a diffusion that we know. So this is a problem which is now not necessarily a problem in any sort. It's a one-dimensional problem. We have a diffusion, and we want to compute its surviving time. So I'm not sure everybody is familiar with this kind of method, how to compute the surviving time. Surviving time of a diffusion. So I will explain it in the last 15 minutes. So now I have a diffusion, that's this one, or anything else, and I want to compute its surviving time. So what you do is that you look, so let's call f of xt the probability that it survives, so it survives longer than t. So starting at x. Okay? The thing that this quantity, I'm going to be able to compute it because it's solution of a very nice equation. Let's assume for 2 minutes or even 30 seconds that my diffusion, it was Brownian motion. Do you know what is the equation that solves this quantity? Something you know pretty well. That's a heat equation. And I'm going to do it in this case, but you will see that that's something completely general for a lot of diffusions. The surviving time solves a very nice equation, which is exactly generator of your diffusion equals the derivative in time of this function. So exactly the heat equation. So how do you do that? Now you start to understand how you make PDEs rising in diffusion theory. You use Ito formula. So you try to find martingale, and you say that the drift equals 0, which gives you exactly an equation. So here, the nice martingale to look at is this one. Times, it's indicator of surviving more than S. So what does it say? It's exactly, the martingale is exactly saying, I survives more than S, times longer than S. And at time S, I look where I am, and I look at the probability that I will actually survive during t minus S, a longer time. And so this thing, when you think about it, MS is exactly the expectation that you survive. So let's call tau will be tau x is the probability of is the heating the surviving time. MS is exactly equal to that. So how do you prove that? You just divide this thing. You say that the indicator of tau x bigger than s times the indicator of tau starting at yxs of the surviving time being larger than t minus s. So this thing is fs measurable, so you can let it go away. And this thing, it depends in fs only by the fact that you start at ysx. So this is exactly the probability starting at yxs that tau is larger than t minus s. So it's exactly what we called f of yxs t minus s. So this is ms. So because ms is the expectation with respect, so is a conditional expectation with respect to a filtration of some random variable, it's a martingale automatically. You have nothing to prove. So this is a martingale. And I'm sorry, I know that I'm going too fast, but the thing is, I don't have a lot of time anymore. So now it has been like many times that we do that. So let's assume that f is smooth. And that's actually, you can prove it using only diffusion theory. Then you can use Ito formula to deduce that f of, so ms, which is f of yxs t minus s, it's equal to some drift term, so let's say dms perhaps, so some term which is a martingale, and I will not write it, plus terms that are in dt. And so these terms, in ds, sorry. So this term in ds, there are three of them. There is one term which is due to the square of the dbt, so it will be 6. So there will be the 1/2 of 6 times the double derivative of f. There is one term which is due to the first derivative, but the drift term of the diffusion itself. So it will be cotangent of yxs over 2 times the first derivative. So you see I was even too confident about the fact that it was a nice formula. And there is a last term, which is due to the time derivative here. The time derivative is minus times the derivative with respect to t. The fact that ms is a martingale, so that this thing must be equal to 0, almost surely. And here there is a small assumption, which is I know something on yx. 1x, so the diffusion, can take whatever value between 0 and 2 pi. There is no restriction. It's a continuous process, like Brownian motion. You can get whatever you want. So this will exactly translate into this formula. This will imply this formula. And for people that are used to this, this is the infinitesimal generator of your diffusion. And I have a z, which is? Oh, writing larger, sorry. For all x in 0 to pi, I'm sorry, and every s greater than 0. Okay? What I have done here, I didn't use anything about the, I didn't write anything about the diffusion process, except that this part is due to this process, and it's exactly the infinitesimal generator. You do that with any diffusion, you will get exactly the same, by following exactly the same lines, you will find the heat equation exactly in the same way. Okay, so this is completely standard. And so now I have a function. I have an equation with boundary conditions, and the boundary conditions are easy to derive. F of x0 is equal to 1. I will not be killed at time 0. And f of 0 t, it's the same thing as s of 2 pi t. It's 0. Yeah, 0. So actually, here you should take the limit, but let's say. So you have a function now. You have a nice equation, a PDE, and you know the boundary conditions. You just need to derive your function. So in the case of the heat equation, you know how to do that. You use Fourier series, and if you want just the estimate when t goes to infinity, which is exactly our case, we only care about the estimate when t goes to infinity, you only need to look at the smallest eigenvalue, because all the other one will be killing your part of the series, of the Fourier series, much faster. Okay? So here there is two roads to take. Either you just say that's Fourier analysis in the case of this function, of this infinitesimal generator, or if you want a self-contained proof, what you can say is, okay, I take the biggest eigenvalue, I take the smallest eigenvalue, which corresponds to some eigenvector, and I check that this eigenvector is exactly going to 0 at the speed I want. So it's exactly what I'm going to do. I'm going to cheat and not use Fourier analysis. I'm going to directly modify my function in order to be caring about only the highest eigenfunction. And so the idea is the following, is that you can define another function which is not harder, which is the expectation, this time not of the indicator, or perhaps I should not. I'm going to keep the event, but instead of looking just at this indicator, I'm going to add a new term here, which is the first eigenvector. And the first eigenvector in this problem is the sign of x over 2 to the 1/3. So why do I do that? Somehow I'm just saying, here if I wanted to solve with this function, I would need to decompose it with respect to all the eigenvectors. I would really need to do the expansion in Fourier series. And I don't want to do that. So what I'm going to do is I'm going to modify my function so that its decomposition in Fourier series is trivial. It's just the first term. And the way to do that is exactly to consider the first eigenvector. So this sine of x over 2 to the 1/3, it appears here just because that's the eigenvector associated to the highest the smallest eigenvalue. Or the highest, I mean, depends how you look at it. Okay, so this is a function which is almost like the other one. I just modify it a little bit. And actually, this thing, this part, is exactly the same. I can do exactly the same computation with this function. So this function is solving the same equation here, but with different boundary conditions. The boundary condition will be still 0 here, but in this case, instead of having 1, I will have sine of x over 2 to the 1/3. So instead of having to decompose this in Fourier series, I have directly the first eigenvector. So I have a Fourier series which is trivial in this case. So when I'm going to solve that, this thing will be very simple because, so why do you do your expansion in Fourier series to get exactly, because each term is very simple to compute. Each term is exactly of the order e to the minus the eigenvalue associated to the eigenvector times t times the eigenvector. And here, in this case, the eigenvalue is 1/4. So if you don't like my explanation, and I won't mind because that's very, very messy, but you can see it another way. This function, it solves the equation with the same boundary conditions. So this equation, this function, is exactly equal to this one. That's the only thing I'm saying. If you don't like the explanation, just assume that I'm a magician. I give you this function, which solves exactly the same boundary condition as the other one and the same equation, so they are equal. Okay? But now the thing here, perhaps you can ask me why do I take the highest eigenvector? I could have taken whatever eigenvector I want. Where does it fail? Because obviously it's of order e to the minus 1/4 of t and not e to the minus, I don't know, 7/4 of t. So where is the trick here? And the trick is that this function here, this eigenvector, it's positive. And that's the only eigenvector which is positive. Think really to your heat equation. So you have the sine and the cosine are the eigenvalues. So the first one is like this, but after you start to have more and more oscillations. There is only one eigenvector which is positive, and that's this one. So how do you conclude the proof in 30 seconds? The first thing is to say this thing is smaller or equal to 1. So this thing is smaller or equal to f of xt, which is exactly the probability I wanted to have. And the thing here that you will have to trust me is that this thing, it's not close to 0 when you are not close to the boundary. So the only thing you need to check is that even if you assume that your diffusion is surviving until time t, it will not be necessarily on the boundary at this point. It will be somewhere in the middle, and this thing will be of order 1. So it will be, say, greater than 1/10 with probability, conditional probability 1/10. So here you can have actually the other inequality up to some constant. So the final thing is that this thing is of order of the probability that you don't disconnect 0 from e to the ix until time e to the t, which gives you exactly, until time t, sorry, which gives you exactly that you don't disconnect e to the ix from 0 before hitting e to the t. So here you have e to the t to the power minus 1/4. So you exactly get that if here you replace by epsilon, you get that this is of order 1 over epsilon to the 1/4, epsilon to the 1/4, sorry. Okay, so you have your critical exponent here. So the story was perhaps a little bit messy by lack of time, but the story is always the same for any critical exponent. You have this discrete word, which is a fancy word I like, and after you have the computation in SLE, which is finally simple, even if I didn't get the idea here, which is really you find a diffusion which is correlated to your event in the sense that if it reaches, say, 0 or 2 pi, it exactly means that you don't have your event. So you translate your event in terms of the heating time of your diffusion. And after this diffusion, you compute what it is exactly. And here is completely straightforward theory, or not completely straightforward, but say classical theory, that you can compute the heating time of the surviving time of a diffusion just using Ito formula and classical theory. It solves some PDE, and you have to solve this PDE in order to conclude. That's the only thing. Thank you.